Now we learned about dot product, and we saw that there is a very useful um, relation between angles of the vectors and the dot product. It also tells us when two vectors are perpendicular. Now this idea of being orthogonal or perpendicular is very important for vectors. And that brings us to the motivation for cross product. The motivation is given two vectors A and B, can we find a vector C that is orthogonal, that is 90 degrees, or perpendicular to both the vectors. Now that's not possible in 2 dimension, but it is possible in 3 dimension. How is that? If I have A and B, right, what you can do is imagine that you construct a plane, right? If you have two vectors, you can always make a plane. And if you have a plane, you can always find a vector that is perpendicular to both A and B. And so, because this angle would be 90 degrees and this angle will be 90 degrees. So it is possible to do that. And it turns out the way to do that is by using what is called the cross product. Right? So this can be done using cross product. Okay, so given vector A as A1, A2, A3, and vector B, B1, B2, B3, we define vector C as vector A cross, so just like the word cross, it's a cross product. A and B is given by the determinant of this matrix, whose first entries are ijk, then you have A1, A2, A3, and B1, B2, B3. Okay, so let's look at a quick example. Suppose we have a vector 1, 3, 4 and another vector 2, 7, -5. Let A be, or let C be A cross B. Then what is C? Well, here is so you have I, J, K. You list down the vector A, you list down the vector B, and recall that for this you have I, determinant of 3, 5, 7, -5, minus J, determinant 1, 4, 2, -5, plus K, determinant 1, 3, 2, 7. So you have I cap -15 minus 28 minus J cap -5 minus 8 plus K cap 7 minus 6. So this is a -43I plus a 13J plus K. So just by definition, because there's an ijk in the determinant, you will always end up with a vector. So this is a vector multiplication. Now check. Is vector C orthogonal to A and B? Well, I will check for A, and then you can try it for B yourself. How do we check that? To check orthogonality, all you have to do is take the dot product. So if I dot -43, 1301 with 1, 3, 4, let's see what we get. Get negative 43 plus 3 times 13 plus 4, which is negative 43 plus 39 plus 4, which is 0. So yes, it is perpendicular to A. And if you do the same thing for B, it will be perpendicular to B as well. Okay, here's another example of a different kind of problem. Show that if you take a vector and you cross it with itself, then it is equal to 0. So what's happening here? Let's see. Well, let's call this vector a1, a2, a3. Then in finding a cross a, I actually have this I, j, k, and I have identical entries here. So what happens is, when you break this down into the order 2 determinant, you end up with identical structures. So you have I cap, you have a2, a3 minus a2, a3 minus j cap, a1, a3 minus a1, a3 plus k cap, a1, a2 minus a1, a2. So all of this becomes 0. So if you cross a vector with itself, you get 0. Just as with dot product, there are some properties. Properties of cross product. 1. The vector given by A cross B is orthogonal to both A and B, which makes sense, right? That's how we define that, or that's how we found these. Second property, if theta is the angle between the vectors A and B, then the length of the cross product A cross B is given by absolute value of A, absolute value of B, sine theta. So there is a nice sort of completion here, because if this was cosine theta, then that was basically the dot product. Whereas if it is the sine theta, it becomes that's the magnitude of the cross product. Third result, two non-zero vectors A and B are parallel if and only if their cross product is 0. So we have results similar to the dot product, where dot product being 0 means that the vectors are orthogonal, and here the cross product being 0 means that the vectors are parallel. Why is that? Well, sine theta is 0. So sine theta is 0 when theta is 0. And an angle of 0 means they're parallel. The value, which is the length of the cross product is equal to the area of the parallelogram determined by the vectors A and B. Okay, so the value also has, instead of it being projection for the dot product, this one gives us areas of parallelogram. Now, there's a cyclical property for the different component vectors. If you go I cross J, you get the vector K. If you think about it, these are the X, Y, Z axis. They're all perpendicular to each other. So if I cross I and J, that's the X and Y axis direction, then what's perpendicular to X and Y axis? That's the Z axis, and that's why we get K. Similarly, if you cross J with K, you get I, and if you cross K with I, you get J. But if you change the direction, J cross I, that's going to be negative K. K cross J is going to be negative I, and I cross K is going to be negative J. Another way to remember this is I, J, K, they form a cycle in the forward direction. So I cross J gives you K, K cross I gives you J, and J cross K gives you I. But if you change the direction, it becomes negative. Then we have certain sets of properties. Now, if A, B, C are vectors, we have, if you take A cross B and you take B cross A, they are never the same. But there is a relation. One is exactly the negative of the other. So they are 90 degrees. The vectors just pointing in two different directions. Oh, sorry. B, you have a scalar times a vector and you cross it with another vector, then it behaves nicely in the sense that it's the same as different distributions of the scalar. The next property is, how does it behave with addition of vectors? And it behaves fine with, it behaves as you would expect with addition of vectors, in that it distributes. And the order, and even if you change the order, it still distributes, but you have to maintain the particular given order. How does it behave with the dot product? What if I take cross product of B and C and then I dot it with A? Then it turns out this will be the same as A cross B dot C. And the last one is, what about cross product of cross product? This one is slightly different. This becomes a dot product magnitude of B minus another dot product C. So these are some important properties. Let's look at an example. Suppose you have a question which says, find a vector perpendicular to the plane that passes through P, Q, and R. Okay, so what is this saying? It's saying that I have a point P, I have a point Q, and I have a point R. Think of 3 points in space. I can join them, right? And I get a triangle. And this triangle can be thought of as a plane, right? It's a plane surface. If you extend it in all direction, it's a plane. I'm trying to find a vector that is perpendicular to this. So I'm trying to find something that makes a 90-degree with this plane. And I know I can do that with cross products. All I need now is 2 vectors to cross. So I can take this vector and I can cross it with this vector. To find the vector PQ, I just have to subtract one from the other, right? So I get 1 minus negative 2, 4 minus 5, and 6 minus negative 1. And suppose I want the vector QR. By definition, I guess we should go from Q to P. So 5 minus 4, negative 1 minus 6. And then QR is R to Q, so 1 minus negative 2, negative 1 minus 5, and 1 minus negative 1. So this is negative 3, 1, negative 7, and this is 3, negative 6, and 2. And then I can cross these vectors to get the perpendicular vector. So I have I, J, K, negative 3, 1, negative 7, 3, negative 6, 2. So I, and then it's going to be 2 minus 42 minus J, negative 6 minus negative 21 plus K, 18 minus 3. So I have a negative 40I, a positive, negative 6 plus 21 is negative 15. Positive 15J, becomes a negative, sorry. And a 15K. So this is the vector that is perpendicular to the plane that contains those 3 points. So that's sort of an application to these kind of things. The last thing that I want to go over is triple products, which we saw as one of the last properties here, number 6, E and F. The scalar triple product A, B cross C is also given by the determinant of this matrix. It's A1, A2, A3, B1, B2, B3, C1, C2, C3. And the the magnitude of this vector is the volume of a parallelepiped. A parallelepiped is a 3-dimensional equivalent of a parallelogram. So if you have vector A, a vector B, and a vector C, then this magnitude here represents the volume of a parallelepiped. So sort of we can see the relation here. When we had the cross product, it was the area of a parallelogram. And when we have a triple product, it's the volume of a parallelepiped. So that brings us to the end of cross product. Um, we will be using this for finding equations of lines and planes in the next topic.